It's really an honor for me to be here and be part of this 50th anniversary event for CIMMYT. I've been looking forward to it for a while. We've heard quite a few personal reflections over the last few days, and I want to start with one of my own, and I'm going to start with a confession. And that confession is that I love technology. And I love biological technology. I've dedicated my life to it for the last 30 to 40 years. But it's not the technology per se, it's the technology and the impact that technology can have on agriculture that's motivated me for the last 35 to 40 years. And so today we're going to talk about a game-changing technology, what we call CRISPR-CAS, advanced plant breeding. And what's exciting about it is that it is truly a game-changing technology for crop improvement. But it's also one that I am convinced can be incredibly impactful on delivering value and solutions to the customers, the smallholder farmers that our organizations want to serve, both in the private sector and in the public sector. So for the next few minutes, I hope I can convince you why you also should come to love CRISPR-Cas technology. So let's see. All right, this is a pretty wordy slide, and I apologize a bit for that, but you can scan it a bit while I'm talking. And it's really about what's the meaning of this technology? Why is it important? And it starts with the what and the why at a pretty high level. And as we think about the technology, Pioneer has been working for many, many years on improving breeding systems, and we see this as fundamentally one of the next tools in the breeding arsenal. It's a fundamentally efficient and targeted plant breeding technology. It enables us to bring solutions to our customers, large-holder growers, smallholder growers, really efficiently, particularly in times of rapid change, when the demands for crop improvement are changing all the time. So the why, in many ways, is a very broad one that we're all familiar with. And so I'm not going to dwell on that. We obviously, as we talked a lot about here, have major goals on improving nutrition and providing calories for smallholder growers around the world, lifting growers up. The what about CRISPR, again, is a focus on working with native characteristics available within the crop. So we'll talk about the idea that we're working here with genome editing and working only on corn genes in corn and rice genes in corn, and rice genes in rice, just checking, and focusing on native characteristics we can find, in any case, in general, through breeding approaches. So let's put this in the context then of the long history of breeding improvements. And so I'm going to put this in the context of the Pioneer lens, but the same lens is true for many other companies and for the history of breeding. This gives a little perspective on modern plant breeding, which from the Pioneer lens date back to 1926 with the first development of a corn hybrid. So, Pioneer started with a revolutionary technology, a game-changing technology, which is moving from open-pollinated corn to hybrid corn. And we've continued to work with hybridization as a core tool for crop improvement. And so you can see by the arrow that we know this will continue for a long time. And of course, you can look back, we talked about Henry Wallace in the last couple of days, the first hybrid of copper cross, and you can see a lineage of new varieties over the next ensuing years, and all of that based on continual improvement in technologies and breeding systems to bring forward these new varieties. And it includes varieties like Aquamax, which I think Mark may mention, improved oil quality with Plenish, and then, and of course, ag biotech was the next wave, you might say, for crop improvement, and Martin talked about that. And that's obviously been very important. And now we're looking at a third technology that we think we may look back on in several years as equally game-changing to those first two, to hybridization and to agricultural biotechnology. And it will build on the foundation of these other tools for breeding systems. So let me just step back a little bit and try to give you a little flavor for what this technology is and how it works and how we see using it as a breeding tool. So I want to start with one important point, which is that CRISPR-Cas as a fundamental tool can be used for many things, as can many technologies. And one of those, you may have heard about, is to get more precise targeting for transgenesis, for biotech traits. And so clearly that's a tool that we will no doubt use in the future as well. But what I want to focus on today is a different suite of outcomes, of applications of the technology. So let me just start with the fundamental point. If you want to edit a genome, and the genome is very large, so a typical human genome has 3 billion base pairs. The corn genome, the maize genome, is of similar size, about 3 billion base pairs. Wheat's about 17 billion base pairs. In contrast, your average text, your average book you might pick up is maybe 250,000 to 500,000 characters in that text. So we're talking about very large text that we have to edit. And so what we need is a search function. And I'll give you a little more, drill down a little bit on that analogy in a moment. And so CRISPR-CAS is essentially that search function, and also as a process of initiating the editing steps that come after. And so there are two components of CRISPR-CAS. One is what we call a nuclease, a sort of scissors that cuts the double strand of DNA in two places at the same location. And so if you look up here, you can see the double helix, and you see the two scissors. And so the nuclease can cut and make a double-stranded break. But the key thing is then, what's the search function, analogous to text, analogous to your word processor? And that comes from the use of a guide RNA. So it's a two-component system, and the guide RNA brings us essentially to the address that we want in the genome to make that double-stranded break. And the double-stranded break is the key for natural repair processes that all organisms have to repair double-stranded breaks, which happen in nature all the time. And so once the double-stranded break happens, the organism will repair that break, and I'll show you the different outcomes of that kind of repair and the different edits we can develop through that on the next slide. But I think I wanted to make one more point here, which is that I talked about the maize genome, the human genome, and the wheat genome, and it's true for all genomes. They're very dynamic. There's no single corn genome. There's no single wheat genome. There's not even a single size for all the genomes we work with. So you must bear in mind that these are very dynamic texts that we're working with when we edit genomes. So how do we use CRISPR-Cas? And so this slide is a little busy, but it's showing you delete, you might call it a delete function, an edit function, and a replace function, both using a text analogy and then showing you a gene in a typical genome. So let's talk about the text for a moment. Just as you're going to address in a word processor and try to find a location you want to edit, you can go in and change a word and delete a word. And so you can clip out, for example, in a sentence like the plant does not have a desired output, we can clip out the word not and end up with a genome in which the plant does have a desired quality output. And so I mentioned the scissors. We can use one single pair of scissors to cut once, or maybe two pairs of scissors that will cut twice and delete out an entire gene at one step. And so we can delete a gene, and we can actually delete many genes at the same time. And one of the really attractive features of CRISPR-Cas is a very powerful technology, is the ability to change multiple genes at the same time. There have been reports in plants of around 10 or more genes at one step that we can change, which is very important. At the same time, we can also edit. So for example, you may have a phrase like the plant has tolerance to drought, and we can modify that text to say the plant has high tolerance to drought. And editing, in this case, would be to initiate that process, but change only one character, one base pair in the genetic code of that plant. And so that's a much more subtle change. And finally, we can also replace. And so I talked about the genomes being very dynamic. It's very common to have a genome that may be sensitive to disease and doesn't even have a gene for disease resistance, but at a certain location in another organism's genome, another crop genome of the same variety, like corn, you'll find a disease-resistant gene. And so you can actually search for the location in the sensitive variety and put that resistance gene exactly where it should be. The same sort of outcome you can develop through breeding, but we can do it in a single step. And so just as you can edit and replace a word, you can replace a gene sequence as well. Let's put this in the context then of breeding. We announced yesterday the partnership with CIMMYT, between Pioneer and CIMMYT. We talked about MLN disease as a first target of ours. And you can look at these two plants on this slide and think about, say, a lower quality plant resistant to disease as a variety that Prasanna and his team might find in the gene bank that has resistance to MLN, but looks nothing like the really productive varieties that have been distributed in Kenya, for example, that are sensitive to MLN, which you can think of as that plant in the middle, one that's sensitive. And so typically, when you want to make that highly adapted Kenyan variety resistant to MLN, once you found the gene, you have a long series of steps, and if it's more than one gene that's required, those steps of back-crossing can take quite a lot of time. In contrast, in a single step, maybe 1 or 2 cycles, you can immediately move those genes for, say, MLN resistance, whether there are 1 or 2 or 3, immediately into the elite variety. And that's the really elegant feature. The same outcomes as you would get from breeding, but done very efficiently to more, in a more responsive way to bring, say, resistant varieties to our smallholder growers. Now, ultimately, no matter how much I love the technology, or maybe you love the technology by now, and as Martin said, it's not a simple story of getting social license for the technology. And we've been very aware of this at DuPont Pioneer. We spent a lot of time talking already to a number of stakeholders. You can see here just a picture of some of the types of groups we're talking to about the technology, listening to people, as well as explaining the technology, trying to understand how they may think about the technology, what concerns they may have, and trying to make sure that this really valuable technology for developing world smallholder farmers, as well as developed world farmers, that actually gets used and adopted. We know the time frames for delivering new products can be relatively short, and so we think it's really important to get this right, and we're working very hard to do that, partnering with groups like CIMMYT and others to talk about the technology in a right way and have a very transparent dialogue with many, many stakeholders. So thanks for your time today.
Neal, given Pioneer's taking an open innovation approach with CRISPR-CAS, what advice would you give to people that are really looking at this technology and working with Pioneer? I mean, what do they have to have in place to really take advantage of this to really have impact?
It's a great question, Mark. So, we are developing a lot of capability, and we are, because we want to enable others, we're willing to work with people with all kinds of experiences to start with, right? Whether you have great molecular biology in your labs and can do this yourself and we can help you do it, we're open to that. If, on the other hand, what you really want to do is potentially get from us an allele already put into a great variety, we're open to that as well. So we want to really have dialogues, come with your ideas, how we can partner together, and we're very open to that conversation in many different models.